Hello, testing 1, 2. Can you hear me? Hello, can you see me? Great. Where's your audio? Do you have a microphone?
Can you hear me?
Yep, just fine.
Great.
Okay, so yeah, I guess let's start. So hello, I'm Arturo Slives. I work at Daniel Productions. And yeah, today I'm gonna talk about the whole thinking and functional mindset thing, because at least from my own experience, when I started doing functional programming, I've been programming in imperative languages, object-oriented languages, for quite a long time, 6 or 7 years or something like that. And it was quite hard to start thinking functionally. And I'm going to share my experience with that and how to cope with that. So at first, I guess we need to understand why functional programming matters and why should we pursue it. By the way, if you have any questions at any time on this, just ask.
Okay, thank you.
Yeah. So personally, for me, functional programming is about making programming easier. And it makes programming easier by reducing the number of bugs I write. And the less bugs I write, the less time I need to spend to debug it, and the less time I need to spend writing tests that would catch those bugs. It kind of also makes you use your brain less in some situations. So if you write your code properly in statically typed language, in statically typed functional language, sometimes writing code just feels like assembling Legos. Pretty much, it pretty much feels like, if the types align, the code does what it's supposed to do. And functional program is really better at reusing stuff, reusing the bits of code that you already have rather than re-implementing it. Because functions are inherently composable. If you have a function and it only accepts some inputs and produces some output, it does not rely on some external state or some magic injections, stuff like that then you can use it in any context. And one of the hard things when coming to functional programming is understanding all the abstract stuff that is already out there that you can use, and without rewriting it. And you can rewrite some of it, and that's just fine. But later, sometime down the road, you just kind of discover, oh, look, the stuff that I've been writing was just a writer monad, and it has been there all along. So that's a fun thing as well. And functional programming makes life easier, pretty much, in my opinion, probably because it has this property of referential transparency. And what that means, I don't know, remember high school, like 8th grade or 9th grade, when you started doing math equations, right? And when you're doing a math equation, pretty much you had this complex equation, and then you kind of solved a part of it, and then you know the value of that solved part, and then you can just substitute the complex part in the original equation with the easier part, with the solved part, and that doesn't change the equation. So you can swap out parts of equations with simplified versions of them. So this is the same idea, and basically if you have pure functions, functions that do not do side effects, you can swap out their calls, their code, with the values that they produce. So we have a function f here, which just takes some two integers and adds and multiplies them. And if we pass 5 and 10 to them, right, we will always get 55. And if we pass 3 and 4 to them, we will always get 15. What that allows for us, it allows equational reasoning. So if we have a program where we have two function calls, right, with these arguments, and we know what these calls produce, we can just exchange the calls with the values that they produce, and the program is still the same. And addition is also just a function that takes two things, so we can change that with its result as well, and we can see that the programs 1, 2, and 3 all produce the same result. While if we have something with side effects, let's say println is a function that takes a string and produces a unit. Unit being this kind of a useless type. It's kind of a nothing. So println has side effects. When you call it, it prints something from the console. And if we write a program that prints out hello world, we can see that it returns a unit, and we know that println will always return a unit. But if we write another program which just has the returned values, 2 units in this case, here, we can see that the hello world is not printed anymore. So you cannot use equational reasoning to think about programs. And this gets even more interesting when you're thinking about when you're dealing with state, especially global state. Let's say in this code we have these two methods, A and B, right? And they kind of modify this counter and then do something with it, return a value. So if we have, every time we initialize, we reset the state to 0, and if we call A, we get 2. If we get B, if we call B, we get 6. If we add these, we should get 8, and we get 8. However, we cannot just change values back to method calls, because then if we call A plus B, we get 11, right? Because A and B now has some side effects to them. And what's more important is that plus is a commutative operation, so it means that it doesn't matter if you do A plus B or B plus A, as long as the values are the same, you get the same result. However, you do not in this case. And this illustrates the point that, this is a simple example and you can track down what's happening pretty easy, but it illustrates the point that perhaps in real code, A would be one method and B would be another method, and somewhere deep down the stack, it modifies some global state, and then you move some methods around, and it suddenly breaks because it's not called in the same order anymore. And this is a source of bugs. So when we're dealing with imperative mindset, we're used to thinking in objects, objects that have private mutable state, or if you're writing C, you might be just dealing with data and procedures that modify that data. However, and you're used to dealing with mutable variables, variables that you can change, and mutable data structures. For example, if you have a list and you call add to the list, you do not get a useful value out of it. You will get a unit or void or whatever in your language, but the list actually changes, so a side effect happens. While when thinking in purely functional mindset, you should think about data and pure functions that just take one piece of data and somehow returns a transformed version of it. You should not think about variables, but you should think about immutable variables, also known as values, and immutable data structures. So if we have a list and we call add to the list, we get another list out of the function, which just now has one more element, but the original list is still intact. And functions, they do not perform side effects, and we can always tell what the function will do by its type signature. So if it just adds two numbers, there's no way it's gonna, and returns a number, there's no way it's gonna print to the console or write to the database or launch a nuclear missile. We know what it does. So now to the example spot. Functional computations are the easier part of it, and we're just gonna look at a simple counter. So we have a mutable version of it. This is Scala. So we have a class, counter. This is its constructor. It also initializes a private variable count to whatever you say it is. And it has a reader method, getter, and it has two methods to mutate the state, increment and decrement, which return unit, right? As one, subtracts one. Clear and simple, right?
Yes.
If we want to use it, for example, in this make count method, we get a counter here. We read the first count, then increment, read the second count, store it in count 1, etc., do some operations, and then return a vector with the counts that we've read. One thing to notice here is the counter that we use is always the same, and once we call increment or decrement, the previous state is destroyed. So if this line of code wasn't here, there would be no way to know what the previous count was. But for the usage, we create a counter, we call a method, and we print out the results. If we're doing it immutably, now we have counter, but instead of a variable, it has a public field, a public value that says count. And once you create a counter with a certain count, you cannot change it anymore. Instead, what increment decrement does now is they return new counters, and they return new counters where the count is either +1 or -1. So when we use it, we get a counter, and then when we do the operations, we create new counters. C1, C2, and C3 is 3 new counters, and instead of returning just the results, we return the new state, the new counter as well. So we return the C3 here, and then when we want to return the counts, we can just take them out of the counters that we still have. And when you use it, you create a counter, you pass it to make count, and you get the newest state and the result out of it. Any questions here?
I'm thinking about this. What happens into the stack where the values are saved. I don't know how it works in Scala, but in OCaml you have when you define a function, you have its environment of definition, and so it takes values inside this environment. So in the part of the stack below. How is it in Scala? How does it work?
I'm not sure what do you mean by the environment here. Can you type an example or something?
Let me think a moment about it. Let's say I declare, I don't know, I'm typing it in the chat. Let a equal 3, and then I define a function that is let double, and it does 2 by a.
Oh,
Okay.
so you're talking about closures.
Then let's say I change the value of a. I don't know, I redefine a. I say let a equal 3. Now I call, if I call double, what value of a is it using? Oops, I redefined a with the same value, sorry.
Yeah.
Let's say I do let a equal 4.
Yeah. So in Scala, you couldn't do that, first of all, because A is already bound, unless you're working in a REPL. But if you're talking about, carrying the A value around in a closure, so yeah, that would if A is just it depends in Scala. So if A is a method, right? So yeah, the thing is that you cannot redefine A. How can you redefine A in the same scope? OCaml shouldn't let you do that unless it's a variable. Is it a variable?
Yeah, it is a variable. It's
okay. So yeah, that's the thing that you shouldn't do in functional programming. To be honest.
okay.
You can do that in non-pure languages like Scala or OCaml. So you can say, yeah, var A equals 3, and then define method double equals 2 times A, and then say A is equals 4. And when you call double now, it will return 8 because it has A as a part of its closure. But this breaks the referential transparency. That means that if you call a function with the same inputs, so in this case, double has no inputs, or in some of the languages it has a single unit input. It should always, with the same inputs, it should always return the same output. And for example, Haskell wouldn't let you do that because it doesn't have variables per se.
Okay.
So, yeah. In Scala, you can do that, but you're kind of breaking the functional paradigm here. And if A is a value, then you cannot redefine it, thus there's no problem with that.
Okay.
Yeah. Shall we go on?
Yeah.
So functional computations are pretty simple when you think about it. You can always replace mutating state in place with constructing new objects with a new state. While functional input-output is a bit tricky when you think about it. The thing is, I/O always side effects. So if you write to disk, or you output something to the console, or you put a pixel on screen, or you launch a missile, you're affecting state, outside state. And if your program calculates something but has no way of interacting with the outside world, it is pretty useless, right? So even when doing functional programming, we need some way to deal with the I/O, but such a way that we don't break the referential transparency and equational reasoning that comes out of it. So we're going to take a look at the simple program as sort of a FizzBuzz. Basically, it just this is an imperative version, and basically what it does is just kind of starts, tells you to enter a number, reads your input from console, and then if you've entered done, it just quits. If you've entered something else, it looks if it's a number. If it's a number, it does some maths and prints out appropriate, FizzBuzz or FizzBuzz. And if it's not a number, it says it was not a number, and then reads another line, prompts for another line. So in imperative version, it's pretty easy. This is the main body of which gets executed when the app starts. We define a variable. We define a method to read a line from a user. We read the first line. While the line is not done, we try to pass it to int, try to print something out. If it was not an integer, we print out that it was not an integer, and then we just read another line and loop forever until someone types done in. So this is clear, right?
Yes.
Now let's rewrite this in functional manner. So the first thing that usually functional languages have this integrated into purely functional languages, definitely have this integrated, but even if you're using something like Scala, there's libraries that already have this written better. But this is a very simple example how to perform side effects and keep referential transparency. So the idea is that something like println naturally will have to perform side effects sooner or later. But we still want to keep the property that if we call println of ours, and get something out of it, we should substitute that something, substitute the call with the value that we got, and the program should still be the same. So essentially, the solution is to functional programs are kind of built like equations. So when you start the program, it sort of builds its own tree in runtime, things that it will do. And then once it has this program as a value, so a part of your program is just a value. And for example, if you have something, part of your program, you can say, do this part 15 times, sort of a like while loop, but you can then operate with program parts as values. So we need a mechanism, a machinery to encapsulate our side effects and make sure that our code is pure. So basically, we write this class later, which just wraps a function, which takes no arguments, and then produces some value, right? And we write a method called flatMap, which takes a value then produced by this, and which takes a function which takes a value and produces another later, and then just returns it. So do not look at the implementation currently. And one more method, which is called end of the universe. In Haskell, it's called unsafe perform IO or something else. But basically, the intention is that you call this method at the last line of your program, and it basically just kickstarts your application into running. And this is a helper that makes the syntax a bit nicer. So we have, in our FizzBuzz, we have some parts which are purely computational. So for example, if we have an integer, we can turn it into a string sometimes, and sometimes there's no string. So the logic is defined here, and this is a pure function, right? It does not do any side effects at all. You just give it one value, and it produces another value, either some string or just nothing, right? Are you familiar with option types or maybe types?
No, I never seen them before.
Okay, so an option or a maybe is kind of, think about it as a type safe null, right? So you could have string, and you could either return a string here or null, right? But you would never know from the type system that you might return a null. Whereas with option, you either return some value or nothing.
Okay.
Right? And it has some useful methods on it as well. Now, when we're doing I/O, we have two operations. So one is reading something from the user, right? So this does not take any arguments from us. So we can define this as a value. We just define a value read, which is this construct we called later. And basically it says when you're gonna call read sometime eventually, it will produce a string. And it will produce a string by executing this code, which is unsafe and does side effects, right?
Okay.
But when you define this, when this code is actually run, I mean, during the first time, during the program construction, no side effects are performed. You just get this later value constructed. And then we have another method that you give a line, and then it tries to parse that line and print something out. And this depends on the line that you give. So this is a method or a function that takes a line and returns this later, which will produce nothing. unit when you call it. And when you call it, it will, do some stuff, some side effecting stuff. So it will try to turn this line to the integer. It will pass it to the into_answer method that we had before. And option has a for each method defined in it, which will call the function that you give. So in this case, print line takes a string, so it will only call this print line if the value is some, and if it's none, nothing will happen. Right? All clear?
Oh, clear.
Sorry?
Yes, it's clear. It's clear.
Yeah, and we have this catch here, which also side effects, right?
Okay.
Now we have that code, and now our main application kind of looks a lot like how we would describe it to a human. So we define a main piece of code which will produce nothing eventually. The lazy here is just a Scala thing because it's the main function is recursive, so you need to add lazy here.
I was about to ask you what that keyword was.
And basically it says we're gonna read a line from the user, right? And then with that value, if it's a string done, we're just gonna produce a unit and do nothing anymore. And if it's some line, we're just gonna print that line, and then we're gonna repeat the main program again. And this is just saying that we don't care about the incoming value, which is unit in this case. And because this is a function from some value to another later, as we saw right here, right? We have a function that takes a value, A, and produces some computation that will occur later. So it takes some value, which we discard, and then produces a computation, which is later of unit, right? So essentially, you define a program like read a line, see what is it. If it's done, we're done. If it's a line, print it, and then repeat, right? Very simple.
Mm-hmm. And what is the question mark at the end of the universe? Is it
bang?
Naming? Yes. The exclamation mark, yes.
Yeah. So it's just a little habit that I've picked up from my Ruby days, and they had these exclamation marks marking methods that are destructive potentially, and that you should use with care. And basically, if we wouldn't have this line here, nothing would happen, right? This would get defined, but because it's lazy and nobody references it, nothing would ever get executed, and the program would quit, and nothing would happen. And Haskell takes this to extremes, because it's a purely functional language. It's able to be purely functional lazy language. And in Haskell, anything that you define is lazy. So you can define a list, an infinite list, and then map through that list. And it says, fine, here's your mapped list. And then you say, okay, take 10 elements from that list. And only then it will actually calculate the 10 elements. And if you try to do that in Scala, if you try to define an infinite list, it would just kind of keep repeating itself until it ran out of memory or stack. So in Scala, you have special constructs called streams, which are lazy lists. Sorry. So in Haskell, it kind of, the programming is a bit different because some things are very, you can write some things very expressive when you know that the calculation would only be performed when it's actually needed to be performed. But in this case, yeah, until we call this end of the universe method, nothing ever happens, and this just kickstarts our program. So it starts running. Okay. So if we see what the definition is it's just we call the function that we've wrapped here, right? And the first function that we've wrapped is read. So it calls this code, produces some value, which is a string, right? And then we used flatmap, and flatmap, so when we used flatmap, we actually, when the end of the universe was called, it entered here, called the inner function, produced a string here, then called this function, produced another later, and then called end of the universe on it as well to keep on executing the program. But the whole thing of this is that now if you just replace this with the value that it produces, the program does not change the meaning. So referential transparency is kept. And you might be thinking that, okay, this is all fine and dandy from academical standpoint. What's the point of all this? And yeah, let's do this.
Great.
So to be fair and square, functional programming isn't always applicable. If you have a Unity game which is running in 60 frames per second, you have to have a very, very good compiler and a very good garbage collector to use functional programming, which unfortunately neither of them, C# and Unity, has. But you still can take some ideas from it while writing imperative code. And if you're writing servers or something in Haskell or somewhere where garbage collection times do not really matter that much, but reducing the number of errors does, functional programming has its uses. So we're gonna model a simple game server, and there's gonna be a world. There's gonna be world objects in it. There's gonna be two types of the world objects. There's asteroids. Asteroids have resources in them. And extractors are built on asteroids and extract resources when you tell them. And the world knows how much resources there are in the world and how much resources we've extracted so far. And obviously, objects can be added or removed from the world, right? So the mutable version of this would be the first part. The mutable part of this would be we start with ID counting. So usually when we write servers, we need IDs to communicate object identities with the client, right? Because a memory address has no meaning in some languages, and you can't send that to the client. Well, you can, but yeah. IDs are fun. So we create a class ID counter. It has a private variable. It has a method that just assigns the ID, changes some state, and returns the ID. We have a world object trait. Traits are interfaces in Scala, but they as well can have implementations, methods defined in them. But basically, we just say that a world object is anything that has an ID, right?
Okay.
we define an asteroid. So an asteroid is just, we have an ID, we have a variable that holds our amount of resources, and we have an extractor. And in extractor, we have this ID here. We have a reference to the asteroid, so that extractor would know on what asteroid it's built and from what asteroid it's gonna extract stuff out, right? And we have an extraction rate, which is immutable. And we have this extract method, which returns an integer, which means how much resources we've extracted. We determine how much resources we need to extract. Basically, this makes sure you don't extract more resources than there is in the asteroid. We subtract the resources from the asteroid, and we return the extracted amount. So far, so good. Everything makes perfect sense, right?
Yes, it does.
So now we have a world. World has a mutable set of objects. It has an inner counter of how much resources we've extracted, a public reader for that. It knows how to calculate how much resources is left. Basically, it just goes through all the objects, sees if they're asteroids, and takes the resources and sums them up. Yeah. So instead of for loop, we have some functional construct here as well.
Okay.
Is this clear?
Yes, it is.
And we have this method turn stat, which just goes through all of the objects. Again, all the extractors, extracts the resources, sums it up, increments the inner counter, and returns how much resources we've extracted this turn. And let's write this little debugging method called extract. We give it a world, right? We print how much resources are left at the start. We look how much resources we had extracted before turn start. Then we extract and print out how much we've extracted this turn. And we print out how much resources we've extracted after the turn start, and then how much resources there's left after the extraction, right?
Okay.
And then we do this. We create a counter, we create an asteroid with new ID and 10 resources, and we create an extractor with new ID, the reference to the asteroid, and extraction rate of 4. We create a world, we add the objects here, and we say, okay, while we have at least 4 resources in the world, let's extract. So the first time there's 10 resources, then there's 6, then there's 2, right? So we enter this while loop. Okay. We print this out. We remove the asteroid from the world, and we call extract one more time. And does this code make sense to you?
Yes, it's very clear.
Yeah. Can you spot anything that's wrong with it?
There is a bug in the code.
Yes.
Show again the code, please.
Well, it's not in this method, but it's in the system.
Okay.
So there will be some unintended behavior going on. But the thing is that you have to think about it, proves my point. So I'm just going to show it to you.
Okay.
And, as we said, 10 resources, extracted 4, total 4, 6 left.
6 left.
6 resources before extracted 4, this turn 4, total 8, 2 left, right?
Yes.
And then we remove the asteroid from the world, right?
Okay.
And, the idea is that if you remove an asteroid, the extractor probably shouldn't extract resources from it anymore.
True.
However, we still have the reference, and we happily say, okay, there's 0 resources left, and we extracted 2 resources from the asteroid, that's not in the world anymore, and we have 10 resources now, and resources left after extraction is still 0.
Not good.
Yeah, so you can see that these mistakes are very easy to make because they rely on side effects and they rely on state. And you can easily, humans just generally are horrible at keeping state in their head.
Yes, you have to keep track of what's happening, and you fail.
So this obviously isn't what we're expecting for. And the fun thing is, in functional version of it, this bug is impossible to write. So the ID counting is very simple. So it's basically the simple counter that we had, right? We have an ID, initial value of 0, and next just returns a new counter, right? World object is pretty much the same. Asteroid has resources now which aren't mutable anymore. So once you've created an asteroid, there's no way to change it, but you can add or subtract resources, and it creates new asteroids with different amount of resources, but the same ID. So the copy method here just changes the resources, but keeps the same ID. The copy method is generated by this case statement. And extractor now, instead of taking a reference to the asteroid, which would be useless because it cannot be changed, right? Mm-hmm. Now takes the ID of the asteroid that it's standing on. And the extract method, instead of being just not taking any arguments, now it takes a world and returns a new world where the state is changed alongside with the value, with the amount of the resources that we've extracted. And what we do, we say, hey world, let's find an asteroid with this ID that we have, and this might fail because the asteroid might not be there. And if this fails, we just say, okay, that's fine. I guess somebody, blown this thing up. So we're not going to extract and return the same world and return 0 resources extracted. However, if we have an asteroid, we do the same thing with calculating how much resources we need. And then we say, we're going to return a new world, which is the original world, but we're going to update this asteroid. We're going to reduce the resources. So this produces a new asteroid, which the world updated, which gets passed to world updated. And this produces a new world. And we return the amount that we've extracted here. Is that clear?
Yes, but what happens in memory-wise? When, for instance, when you copy the asteroids?
So this is the part where I talked about smart compilers.
Okay.
A sufficiently smart compiler will understand that you will never use the old reference of the asteroid, and you will never use the old world, right?
Yes.
And it's gonna pretty much just, it can be free to optimize this to a mutable change in memory. So instead of creating a new object in the heap, it can just rewrite the appropriate piece of memory and be done with it.
Okay.
While if you're writing in Scala or C#, this will obviously create a new object which will get allocated to the heap, and the old object will eventually be garbage collected. which isn't that much of a problem in a game server written with Scala, but is a problem in a game written with Unity, especially with their garbage collection thing, and Unity running client side. Plus, JVM has a generational garbage collecting, which doesn't stop the world, so you can still have a server that does not have these pauses where everything is just stalled by the garbage collection. You can run it concurrently. Okay. So the world now looks like this. We have a helper method that you give a bunch of world objects, and it creates a world, and it creates it from the empty state. And for each world object, it just calls the updated method. This is the world, this is the object. So basically, it just creates a new world, then updates it, and just goes over this and returns the latest state of the world. The world now has an object map, which is a fast way to find, look up objects by their IDs. And it has this extracted state thing, extracted value, which we had as a variable before. It has this find method, which basically just goes to the map, looks things up by ID, and checks if the type matches here. So yeah, this is needed because on JVM, the types in generics are generally erased in runtime. So this A is just gone in runtime, so we need to attach a class tag in the runtime to be able to do this type check. The updated method takes an object and updates the map. So it just says, okay, I'm going to return a new world where the map is where the object map is an updated map where we associate this ID to this object. So basically, add or overwrite an entry to a hash map. And this is, what I've called, this is an immutable collection. So as I've said, add operation on a map does not modify the old map, but returns a new value, the new map. Remove does pretty much the same thing, takes an ID, removes it from the map. Resources left is exactly the same. We define a helper method called objects, just object map values, so we don't have to write it all over again. And the turn start now, I hope you're starting to see the pattern here. Now it's, instead of returning just an integer, it returns a new world and an integer. And what it does, it just goes through objects, collects all the extractors, and folds them. Are you familiar with the notion of folding?
I saw it, but honestly, I don't remember how it works. What is
okay,
the purpose?
So the folding is essentially you have, let's say, a collection, right? In this case, a list of extractors. You give an initial value. In this case, it's a world, a tuple of current state of the world and 0 resources extracted, right? And then you give it a function which takes 2 arguments. So the first argument is this current state that you've specified here. So, you say world, total extracted, you bind these values to these names. And the second argument is the object that you're currently iterating, the object from the collection, so an extractor. So the first time, it just gives you this 0 and the first extractor. And then you call, extractor extract, give this the current state of the world, It returns you a new state of the world, the new how much it extracted, and you return the same type as here. So you return the new world, and you return how much we've extracted totally, and this function just keeps going, being called while there's extractors in that list. So,
okay.
So it kind of folds down a list or some collection to one value, which eventually is a new world and a total amount of resources we've extracted.
Okay.
And then we have this. Then we have this new world, and we just return, this new world, and update that we totally in this game so far we've extracted, this amount, which is the previous amount plus which we extracted this turn, and return what we extracted this turn.
Okay.
Any questions?
No, it's fine.
So yeah, so now when we write our extract method, previously we had a side effecting thing somewhere in this print line statement, right? Now we can just say, hey, world turn start at the start of it. It does not impact the old world. We get a new world out. So we can still say old world, resources left, etc. And now we can say, we can clearly, distinctly see, where new world extracted and old world extracted is used. If you compare this to this code, basically we're calling the same method 2 times. However, it's returning different values. And it's sort of confusing unless you know that this actually changes, yeah. And this might not look like something that changes state. You might not think that it changes state, but it does. And I'm sure that you've experienced this frustration tracking down bugs. Why this value is 5, not 4 at this state of the program? And then you go, oh, somebody did this in here some time ago. Right?
Yes, yes, and you have to start to worry about the meaning of names of methods.
Exactly.
To remind yourself that you are touching the state there.
So yeah, so here we just do pretty much the same thing, but return the new world at the end of it. And when we use it, we create an ID counter. We assign an ID, create an asteroid with 10 resources, create a new counter with the next ID, assign an ID here, give the asteroid's ID, extraction rate of 4, create a world out of an asteroid and an extractor, right? Pretty much do the same thing, but say, world is... So this code isn't pure anymore, and this is a part of Scala that I kind of like, that you can write non-pure code where it makes sense. So in outer shells, in outer layers of the code. So if this main method is an entry point of our program, or for example, in a method, in the middle of the method, in the implementation of the method, and if the state changes does not leak out from the method, if you cannot observe them by calling the method, you can use mutable state as long, if you want, inside the method. And Haskell has ways to do that as well. They involve monads, a specific kind of monads, which are specifically designed to handle mutable state. Their way is nice as well. It's mostly influenced by the fact that there's no notion of variables in Haskell in the language definition, and everything is lazy. So, but here we kind of cheat. We could solve this without a while loop. We could, just write a recursive method here that would pass a new world over and over again to itself. But we've written a variable here, so we replace that variable, remove the asteroid, we do the actual operation, and then we call extract world, right?
Mm-hmm.
And this time we have the behavior that we want. It actually, says that there's 0 resources left, and it doesn't extract anything, and everything makes sense.
Finally working as intended.
Yeah. So this is how functional programming helps to reduce the number of bugs that you write. Basically, some things are impossible to do in functional programming, and it turns out that it's a good thing. So yeah, there's a treat called Scala Z versions, and Scala Z is a library for Scala, which ports a pretty darn big amount of Haskell standard library to Scala. And it's mostly utilities for purely functional programming. So we're going to just skim through these. So the counter, for example, is defined a bit differently. If you've noticed, we had this pattern, right, where we had a function that took some state in and then returned some new state and a value, right?
Yes.
So this, we take some state and return a state and a value, right?
Yes.
So there's an abstraction for that called the state monad, which is defined like this: state of some state type and some value type, S and A. And when we define our counter here, it's just a simple case class. So it basically is just a simple data definition. And then in the companion object, we define some functions to work with it. And this is a helper function, which takes a function from one state to another, and basically says, okay, we're going to have a counter here. We're going to create a new counter by this function f. And we're going to return the new counter, and we're going to get the new value by getting the count out of the new counter, right? So do and get. Does this make sense?
Yes, sort of.
So this is like a helper. So count So the idea is that instead of defining methods, you define functions, which are state transitions. And for example, count is a state transition which does not really change the counter state, but just produces a value, which is count, right? So you pass counter of 3 to this function, right? If you call count.run and pass a counter of 3, it's going to return a counter of 3 and this count, and this count, just 3. Increment then uses our helper, so we use this counter and we increment it by 1. So if you call increment.run, you're going to get, with counter of 0, you're going to get counter of 1 and a value of 1, right?
I see.
And decrement does the opposite. So instead, of writing this helper, we could just write, pretty much we could just write all this code and then piece this little piece instead of this,
Mm-hmm.
and this is equational reasoning at its best. So you can basically, move code around and nothing changes. Whereas if you have state transitions, or for example, if this code would be on a try catch and you moved it here, meaning would change. So in imperative code and with state transitions and with exceptions, code meaning changes based on its position. So in this case, you can see that this is just a simple substitution.
Yes.
And when we use the counter, we write the same program which we had before. So yeah, so we had this, right, where we manually incremented the counter, kept the new counter, etc. So instead of doing that, now what we do is we create a list of operations, of state transitions, which all produce values. So we get the first count, we increment, and decrement, right? And this defines a program. So this currently defines a vector of state transitions, and we call a function called sequence on apply that turns it inside out. So instead of a vector of state transitions, we get a state transition that takes a counter and produces a vector of values. I'm going to type probably the type here. So instead of state, instead of vector state SA, we get this. Can you see that?
Yes, I see.
Yeah. And yeah, now it's a function where you pass a counter, it produces a new counter, and it produces a vector with the values, with the counts that we had. So does this was kind of a hard part to understand for me, because usually, when you call a method, you expect it to do something and return something, a value that is useful, like 5 or 10. But now you have these count, increment, and these are pretty much functions. So you have a bunch of functions, add them to a vector, wrap it around, and now you have a function that produces a vector. So you're creating code at runtime and then using that code to calculate a value.
I see. I think once you get in the mindset, it might be, I can see clear advantages.
So if it's not clear, I can show you. Just a second. I'm going to reshare my screen. Yeah, in the face. Yes, so let's share this.
Mm-hmm.
So we're going to launch console. Just let's so we have support the counter as well. So let's create a counter of 0, right?
Mm-hmm.
And we have these functions, count and increment, right? So as you can see, there are state transitions from the counter that produce an integer. So if we actually call, I think it was called run, you can see that it produces, so for example, if we run the count function, it produces the same counter and it produces the current value. Whereas if you run the increment function, it increments the counter, produces the incremented counter and 1. And then if you say, let's say, okay, we need to count, increment, 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 decrement, right?
Yes.
We have this vector of functions which doesn't do anything, but let's import some helpers. We wrap it around, and the type is a bit scary, but the idea is that when you run this on the counter, now you get the final state of the counter and the values that we had there. Whereas if you would, for example, have these, you could map over the vector and run each function separately. You could see that increment always produces the same value and decrement always produces the same value, but this makes 5 counters instead of 1 and a vector of 5 values. And the neat thing is that the sequence on apply is written for any monad, any monad or any applicative that has an apply type class. This is still a bit cloudy for me, but usually if you have a collection of something, so another use case would be you have, let's say, a vector of futures. So a future is something that's running concurrently, let's say a web request, right?
Mm-hmm.
So you have a list of futures running all together, and you want to produce one future with all the results in the list. So that's achievable very easily with this sequence and apply. So if you have just a list of futures, which are fetching 5 web pages at the same time, and you want to once all of them are fetched, you want to do something with it, you just write list of future 1, future 2, future 3, sequence on apply, and it turns into a future of list of let's say strings, which are the content of the body of the web pages. Okay, let's go back to the presentation. Are you tired yet?
No, just a lot of information to process.
Yeah. So FizzBuzz is a lot simpler because it doesn't have no new ideas. So instead of this thing called later, we have this thing called IO monad from Haskell. And if you swap IO with later, it pretty much says the same. The syntax for here is just a syntax for flat maps. So you can either write this flat map this flat map, map line, or you can write this in a nicer syntax. And when now putting things to console or reading them from console returns I/O actions as well. So they're pure as well, and the library provides the impure implementations. So our read is defined. We put a string. We don't care about the unit value that it produces. We read the line. We map the action and strip the line ending out of the line, and then we just return this line, as the string. And line to print is pretty much the same. We pass the line. Oh yeah, before we had this try catch thing.
Mm-hmm.
In Scala Z, we can there's a function called parseInt, which you give a string, and it tries to produce an integer out of it, and it returns a validation. So either there's some error, and we say that, hey, it was not a number, or we get a value which we then turn into an answer. And if there's nothing to do, we return an empty I/O action, something that doesn't do anything, or we just put it out to the console. So if you take a look, at this code, it's sort of familiar. But the main method is very familiar. So, we read the line, get that line. If the line is done, we return I/O unit. Else we print the line and then do the main method again. And we just return the whole program to the runtime, and then it runs this I/O. The safe app trait makes sure that you need to return I/O unit, and then you return it, and it just runs it and kickstarts your program. And yeah, you can see the similarity here.
And it's interesting that the use of pattern matching in place of the try catch.
So the game is quite heavy to talk about in the presentation, but there's code online if you want to analyze how the Scala Z version looks like. Basically, it involves state monads and some I/O and some state monads. Nothing fancy. So yeah, that's about it.
Very nice.
Yeah. Any questions?
No, maybe in a few days after I processed everything. But I was thinking before you were saying about in some fields it's difficult to use functional programming. What about if I remember well, XNA and now Monogame can be used with F#.
So can Unity. So it can be used with Unity as well. Yeah, but yeah. So
nothing. Just thinking.
Yeah, the problem with the problem is pretty much in the smartness of the compiler and the runtime thing, the runtime costs. So you're constantly creating, objects,
Copies. Yes.
Yeah, copies, functions, stuff like that, and it takes its toll. If you have a constrained system like in Haskell, like where all side effects are explicitly controlled via monads, and special support from the language, then it has a lot of free space to optimize. So, for example, if you call something and it thinks that it's expensive to calculate, and it sees that you are calculating this thing with the same arguments over and over again, it can just automatically cache the value. Or there was this idea, a research project of automatically parallelizing Haskell code. So you just write code and it just magically runs on all the CPUs that you have.
Wow.
So these things are kind of a research projects, but a lot of companies are using functional programming, in a lot of really busy things, just probably not client games, because there you have memory constraints, you have CPU constraints. If Unity had, for example, a garbage collector, which would be time constrained, so if you calculate everything in, I don't know, 5 milliseconds, rendering is another 5, you have 6 milliseconds for garbage collection, and you clean up bit by bit, it would make a lot more sense, I guess. However, currently, if garbage collection hits you, you're kind of dead in the water for 50 milliseconds or 100 milliseconds. But we've used functional principles in our own games, mainly by using generic structs, which are pretty cheap because they live on stack, and functional reactive programming, and just generally, avoiding complex shared state and making everything explicit, making data flow explicit, which you get automatically with functional programming. So you cannot, in functional programming, you cannot, access a global variable and then change it. So, yeah, it's worth learning even if you cannot apply it directly, but it will definitely help you write cleaner code, even in imperative languages.
Yeah, I see. Well, not only it's interesting, but also I have to do it. So I have to do it for school. Okay.
Cool.
And this Scala's library is where does it come from? Is it made by the same authors of or committee that handles the Scala language, or is it external?
No, it's an external effort. Mm-hmm. Some of the people who wrote Scala-Z wrote code for Scala as well, like the infamous Tony Morris, which is a very vocal advocate for functional programming. He's a very smart guy. However, sometimes the way he approaches enlightening you might seem offensive. But yeah, there's also another effort called CATS, so Scala-Z is a bit of a cryptic library, as in it doesn't really have documentation per se in the traditional sense. It kind of goes with, there's papers about monads and semigroups and Claesley arrows and things like that. And, types tell a lot, which they do once you know how to read them. But yes, it's a steep learning curve. There's this guy which wrote a blog series called Learning Scala-Z, and it's been an interesting struggle for me to learn bits and bobs here and there. There's an interesting and very useful book called Functional Programming in Scala, which explains a lot of these things. and how functional design works. How do you design functional libraries, stuff like that. So there's definitely literature. There's a free course in Coursera that introduces functional programming in Scala and functional reactive programming in Scala, which I recommend you take, especially the functional reactive programming, because it has proven to be immensely useful in writing game code in Unity.
Okay.
And making, some sense out of a mess that Unity projects usually turn into. So yeah, there's material out there, and if not Scala, some people advocate just diving in fully, because with Scala you can always fall back to your old sinful mutable ways and do stuff like that. Whereas you can try learning Haskell, and you kind of are forced to do things in functional way because there's no other way.
Another way, so.
Yeah, and there's a free book called Learn You a Haskell for Greater Good, which is also, there's another book I think called Learning Haskell, which you can also try. I've personally never learned Haskell. Unfortunately, I can't find the motivation because we have legacy code that runs on JVM, and also a lot of stuff that Haskell can do, Scala can do as well. And some of the stuff it does better. Like, in my opinion, the syntax for records. So, for example, when we defined case classes, right?
Yes.
There's no problem in defining several case classes with the same names, whereas in Haskell you have problems. So if you define a counter with a name count, it automatically defines a function name called count, and then you have problems with defining another record that has a count field, because functions cannot be overloaded in Haskell, so you cannot have two functions called count, which extract the field from the record, and thus. So it's not a perfect language, but it's definitely something that's worth checking out, especially if you're just trying to get into functional programming. Unfortunately for me, my way into functional programming was just writing Scala code in mutable, horrible way, and then gradually learning the functional way as I moved on.
Do you fall in temptation sometimes?
Well,
like, I'll write something mutable only this time.
It depends on what you're writing. If you're writing a Unity game, obviously you're going to write mutable code. If you're writing something that is that you can write with Scala, I tend to prefer a functional way because for me it's more intellectually challenging, usually faster, unless I stumble upon something that I don't really know how to solve and need to learn. And at the end, the code is clearer and more maintainable.
Yes, more elegant. And
yeah. So there's really no desire to go back to write mutable code.
I see. So thank you for the presentation. When is it going to be the official one?
So I'm presenting this in this hacker camp called No Trolls Allowed on end of July 31st, I think, and August 1st. It's going to be a hacker camp in Lithuania, and it's free, and but you have to register before tomorrow, because tomorrow is the last day, and the only thing that you need to get in is to make a presentation and present it. It can be about anything, programming, building kites, brewing beer.
This is very nice.
Stuff like that.
This is very nice.
Business. Business is always fun. And then I've been asked to present this at Conus Java user group at the end of, at the start of autumn. So, I don't know, September probably. Because we're in. Yeah.
So, best of luck, and thank you again for your time.
Okay, bye-bye.
See you around.